Google wasn't lying, on the Fermi bubbles, on a geometric model for the Fermi bubbles in the galactic center. On this title slide here, I have included the original picture that led to the discovery of the Fermi bubbles here. Not too hard to spot. They are these two massive lobes here, mainly. As we'll get into more detail, they encompass a little bit more than this, but we will get there in due time. In due time, I mean now. Sorry. What are they? Well, they were discovered by the Fermi Large Area Telescope, now renamed the Fermi Gamma Ray Space Telescope, only 4 and a bit years ago in 2010. They are composed mostly of the gamma rays, as it was the Gamma Ray Telescope that actually found it. That's what it saw most in, and they still are mostly in gamma rays. But we have noticed them in other wavelengths such as radio, microwave, basically anything that isn't visible, right? Anything in space that's really cool you can't see. So that's what's happened here. They are only recent, so there are a few theories of where they come from. Not too many, and none of it's been confirmed, so they're still up in the air a little bit. But what are those theories? How do we think they may have come around? The proton-proton collisions in the center of the galaxy lead to one possible explanation. That's where cosmic ray protons in the galactic center, most probably accelerated by a supernovae. They collide and they produce a pion which decays into 2 gamma rays. So that is one possible explanation as to where these gamma rays come from. The other one is inverse Compton scattering. So regular Compton scattering is when a photon hits doesn't have to be stationary, just any electron, and thus transferring some energy to the electron, and the photon loses energy. This is inverse now, so what happens here is a cosmic ray electron, most probably accelerated from those same supernova at the galactic center, will collide with a photon, thus raising its energy to gamma ray level. So those are 2 of the possible explanations as to where they come from, but as I said, they haven't really been confirmed yet. Why are we studying them? One reason is because they're just relatively new, right? They were only discovered 4 and a bit years ago, and people really want to know what they are. It may also lead to help discovering what's happening at the galactic center. And also, similar structures have been found in other galaxies that have just been quite dim compared to the galaxy itself, and because they are so far away, quite small as we see them. So we haven't really been able to study what they are, but these ones are, right in our own backyard, right? They extend pretty much across almost the whole sky. They are very big. Chances are when you look out at the sky at night, you may be looking right up and you just don't know it. Because most galaxies actually display these similar structures, it may be a new step in galactic evolution. I'm just being, just throwing something out in the air there. We don't actually know. They are relatively new, and nobody really knows a lot about them yet. So what do I do while I'm here? So my job, whilst I was here, was to create a full 3D model of these things that encompasses everything we know about them so far. So reading old papers, seeing what they do, so like their how they emit, their shape, what they see. My plan was to create a full model of these things completely. I say my plan was to create them. In reality, what actually happened was this is a very long project, and I only really got out the base of this. So what I have done is, as we'll see, I have gone for the ideal case and kind of seen where it's gone wrong for the next person to maybe tidy it up. So my job was to be wrong, and that was quite hard actually, because it hasn't always gone to plan. I was using MATLAB for most of this, and this was one of my answers. Actually, it wasn't. It was the root of all this was one of my answers. And yeah, my laptop became quite endangered after this, because I almost threw it across the room. Also, this right angle down here caused me a lot more grief than what you were saying for a good part of the month. I don't really have much more aside from to show this picture, really. Okay, let me get on to actually my work then. So what I have been doing, this plot over here is a plot of the vertices from the original Su et al. Discovery paper in 2010. So Su and his team came up with these vertices of the gamma ray parts of the bubbles, and that's kind of what's stuck since. So as far as we're concerned, these are the edges of the gamma ray parts of these bubbles. Extend to 50 degrees up there, and down here it's minus 53.5, I think, is the lowest it goes. So how do I adapt that? Basically, this is the model I've been working with. So it's just the ideal case, so plus or minus 50 degrees, plus or minus 21 degrees across. And they are both completely identical. So you do reset for one, you do it for both. What are the dimensions that corresponds to? They're just shy of the distance to the galactic center in height, and height is from there to there. It's about 70% of the radius to the galactic center across, and that corresponds to the radius of one bubble being about 30%. The reason why I've kept it in terms of distance to the galactic center is because that's up for a lot of debate. It's a bit ambiguous, but whatever you choose, these numbers still hold. If you choose a distance to the galactic center of 8 kiloparsecs, which is quite a good estimate, then the height is at 7.94 kiloparsecs, radius of about 3. So that is the model I've been working with. What have I done with that? Once I got it, I had to test it. So I just threw in these pictures because this is really where the bulk of my work has been. Doing a lot of the geometry. First bit was testing the projection. So how would that model project onto a 2D plane in the sky? Does it fit what we see? What changes have to be made? I also modeled it with the top part being a sphere and the bottom part being a cone. That's how I modeled it. So I've done calculations for both. Felt like a mathematician for a while there. Needed a shower, really. I won't spend too long on this slide here because it's just a lot of formulas and you don't want to see that. But the reason I thought I'd throw it in is because this really is where my work has been. I came up and derived all these formulas for the projection in particular. I came up with more for something else, but I haven't bothered to show you that. Kind of, you guys don't want to see that. So this is the thing of this. These are the formulas I've been working with to get the projection out. Define my own terms. R being the radius, B being distance from the plane to the center of the sphere, so on and so forth. Theta being the angle from the vertical, and stuff like that. But that's all just details. Don't worry about that. This is really the money shot here. This is what the projection looks like when compared to the true projection. So, as you can see, it's not perfect. It wasn't meant to be perfect. Perhaps if you were to introduce a tilt, then it might match up even more, which is pretty cool. That could actually mean that the bubbles are slightly more spherical than we think. As for now, it hasn't quite worked out. But that was expected. I mean, this is just the base. That's what I've been doing. Another cool thing about the bubbles themselves that we can use to test is that their surface brightness, if we look at them in the sky, their surface brightness in gamma rays appears roughly flat. Their curves appear roughly uniform. These are the plots from Ackerman et al. Last year that show this. This here is the north bubble there and the south bubble there. These are all in latitude bands. So this is from latitude 10 to 20 degrees and 20 to 30, 40, 50, so on. Now, take a look at the north bubble here, right? So, I mean, the south bubble, you can see it. You can see a peak in the south bubble. It's probably not as defined as what it should be if it was a uniform volumetric emissivity. So there's still something going on in the south bubble. But what's even more fascinating is that the north bubble appears pretty constant, which is unusual. There are big error bars around here because as we get lower, we get closer to the galactic center, which can be a bit of a struggle to really look at these kind of processes. There's a lot going on there. But as we move away, well, we would think we'd get a better plot of these things. Yet it's still appearing pretty flat, which is cool, which is something else we can do. We don't really know a lot about these things. So knowing that, how would the model compare to these plots? That's the next part of my research. More geometry, more maths. So I came up with this method, the angle away from the center method. Now what that actually means is, first of all, we're assuming a uniform volumetric emissivity from these bubbles. So what that means is what I expected before the plot came out is that we should see brightening in the center and getting dimmer as we go out. Okay, that is actually what we see. I'll show that later. How I went to do that was just using all these maths. So A is now the angle at the center, away from the center, and basically using this equation here, for any longitude and latitude pair, it can give you a path length through the bubble. Because if it's uniform volumetric emissivity, then what that means is the surface brightness should go like the path length. A longer path length through the bubble should mean a brighter spot there. So that was the method I employed. And, that's right, this doesn't work. This is what we get out. So as we see, right at the center is where it's the brightest, and it gets dimmer as we go out towards the edges. Now, this axis over here is distance through the bubble in terms of radius to the galactic center still. If you remember back, the radius of the bubbles themselves were about 35% of the distance to the galactic center. So twice the radius, being about 70%, 0.7, which is right up here, is right at the center. So this model is consistent with that, and this is what we see from the projection of my model. And I didn't, at the time ran out, I didn't have time to make the plots to actually compare them, but what we actually do see is that it's clearly not flat, right? It is peaking as we get to the center. No matter what kind of latitude band we look at, it's doing the same thing. So, that's what I expected. My goal was to be wrong, and I was. That is good, for me anyway. So, this is wrong. How do we fix it? What is there left to do? Well, the next step, I believe, would be to model a shell around the center of the bubble that has a higher volumetric emissivity than the center. And what that will achieve, hopefully, is to brighten the edges such that the surface brightness plot will appear mostly flat. We aren't really sure how thick that is. We're not really sure if it really exists. But it is the next step, and if we can simulate that brightness pretty well to match the plot, then we can be pretty sure there's something going on in there that would give rise to a similar kind of shell. So that would be the next step. And that was all my work. So I would just like to say thank you to all of you for coming. Thank you to Roland for being my supervisor. And thank you to the RSAA in general for giving me this opportunity. I've had a really great time over in Canberra. And perhaps in the future I will see more of you again in a different position. So thank you. No worries. Any questions?
Your model had brightest in the center, so how does that compare with the southern one?
Well, because we're assuming the ideal case, we're assuming that they were symmetric and perfectly the same. So what I showed you there for the north bubble, that would be the same, just reversed for the south bubble.
Sure.
And it kind of did match up for the south bubble. The south bubble has more of a peak in there. But we know from previous research that the south bubble isn't that ideal. So more research has to be done there. But what we kind of do know from that is that perhaps the shell around the south bubble, if there is one, is not as thick, and it could follow a similar kind of pattern to what I've done here. So that would have to be further research, but it's definitely a good question. Yeah.
It seems to me that the shape of it, reminds me of the bubbles around Eta Carinae, and there's quite a bit of work done on this shell. So have you looked at it?
No, I haven't, but I know what you're talking about, and they do look quite similar. Yeah, that would be another great point of research, great place to go to, because they do look quite similar, and who knows, you may find a gem in there. You're right. Yeah. Okay. Thank you.